My name is Emma Dixon, and I will be showing the solution to problem number 17. The figure shows a normal ray incident to the surface from the air, n equals 1, on a thin film, n2. Each wavelength described here is the wavelength in air. Answer the question in terms of delta phi equals 2 pi r. Anyway, question A, consider a soap bubble where n2 is a thin soap film and n3 is air, with n2 equals 1.4, so we can fill that in, and n3 equals 1. Which visible wavelengths experience constructive interference, with visible wavelengths defined as between 400 and 700 nanometers? So I'm just going to draw the picture here, because this wave goes back up like this, or it goes down, and then back up like this. This is the question we're concerned in for part A. And now let's start with the equation delta capital phi equals 2 pi delta r over lambda plus delta lowercase phi. Now, we can substitute some of these with things from our knowledge of it. For instance, we're interested in constructive interference, and we know constructive interference has to be an integer multiple of 2 pi. So we can write delta big phi as m2 pi, where we just know that m is an integer number. And then that is equal to 2 pi. Well, delta r is the extra distance here, so it's 2 times t, and we are given t in the problem. So we can write that as 2t. But this is lambda. We know the lambdas in terms of lambda in the air, but the lambda we need for the problem is the lambda in the wavelength in n2, because that's where it is at that point. But lambda n equals lambda over n, so we can just substitute in that instead of that, and then we can put lambda down the bottom over n, but since we're dividing there, it's much tidier just to write it up here. And then plus the initial phase change. Well, we know that if it's reflecting off a surface with a higher index of refraction, you will get a pi phase shift, and if it's not, you won't get a phase shift. So from air, from n1 to n2, it's from 1 to 1.4, so you will get a pi shift for this. But from here, we're going from 1.4 reflecting off 1, so you're not going to get a shift. Therefore, the total shift is pi, so we plug in pi. Now, we're interested in what visible wavelengths have constructive interference, so we want to be solving for lambda. So that's pretty straightforward. We just cross off pi, this, and then lambda equals 2t n over m minus 1/2. So we're going to start by making this as small as it can be, and then just go from there. The lambda's going to be, lambda's large as it can be. Lambda's going to be at its largest when m is at its smallest. So because we don't want to deal with negative wavelengths, it would be to come out the same, but let's pick m equals 1 for our first value. So for m equals 1, we get lambda equals 2 times 300 nanometers times 1.4, which is 840 nanometers. We'll be using that multiple times, so just write it down now. Divided by 1 minus 1/2, which is 1/2. And then plug that into our handy friend, the calculator, and we end up with lambda equals 680 nanometers, which is not within the visible range. So that's something. So then we go on to m equals 2. And for that, we do the exact same thing, but we do 840. We do, lambda equals 840 40 divided by 1.5 this time because we're just plugging in 1 for the m here. I mean, we're plugging in 2 for the m here. We started with 1. And then that equals 560. Oh, this is nanometers. Sorry. Nanometers, which is within visible range. So this is one of our answers. And now to see if there's another, let's see if for the next point we drop below 400 or not. If we drop below 400, that means it's no longer in visible range, and this will be the only one in visible range. If it is within 400, above 400, we will have to do more calculations. So let's do m equals 3 gives us 840 equals 840 nanometers divided by 2.5, which gives us, I think that's 366. I'm pretty sure that's what I'd written, which is definitely below 400. So this is the only wavelength of visible light that will experience constructive interference under these circumstances. So now let's move on to part 2 of the question. I'm going to erase the bottom part. I'm going to leave that up there for reasons that will become apparent later. And now part 2 of the question says, consider a thin film N2 of a different thickness on a material with an index of refraction N3 equals 1.35. We don't know what N2 equals in this case because we're then asked, if 650 nanometer light has constructive interference, what are the 2 smallest possible values of N2? So let's start by assuming that, so we're going to start with this equation again that I have already written up here. And it's still, because we're looking at constructive, we're still going to get the 2 pi m on for the delta capital phi equals 2 pi 2t again from here, and then the n over lambda, that part hasn't changed. We're going to be solving for n. And now for the initial phase difference, well, we're bouncing off something. It's got to have an index of refraction higher than 1 because it's not air, and air is the lowest. So we're going to have a pi shift here. But here, if we're under 1, if we're picking n is less than 1.35, then we're also going to get a pi shift here. And then you end up doing delta little phi equals phi 1 minus phi 2 equals pi minus pi equals 0. So we can just leave that term out. And now let's solve this equation for n, and that gives us n equals m lambda over 2t. And now let's do the exact same thing we did then. It's going to be smallest when we're looking for the smallest values. It's going to be smallest when m is smallest, obviously. So let's pick m equals 1, because m equals 0 gets an answer that makes no sense. N equals 0, which isn't a possibility here. So then we just get n equals 650 nanometers over 2 times 270 nanometers. And that is equal to 1.2. Brilliant. That's well within sensible range. So that's going to be one of our values, and that's going to be our lowest value of N2. Now let's plug in m equals 2 and see if we can find the next value. But that equals 2.4. Now 2.4 is bigger than 1.3. So then this part that we did the delta phi's with the 2 pi's, that doesn't apply anymore. So we need to switch equations at this point. We can't do anything more with the equation we have. We can't find the other smallest one. So now we have to assume that N2 is going to be bigger than 1.35. If it's bigger than 1.35, we're going to get a 0 phase shift here, and therefore a total initial phase shift of pi. See why I wanted to keep this equation up? We already wrote that equation in the previous section for one with a phase shift of pi. So then we can just solve this for n instead of lambda, and we are going to get m minus 1/2 lambda divided by 2t equals n. Now let's plug in n equals 1 to, again, try to get the smallest value here. Plug in m equals 1. And then we're going to get 1/2 lambda divided 1/2 of 650 nanometers divided by 2 times 270 nanometers equals 0.6. But that doesn't work with this equation because that is less than 1.3, and therefore we wouldn't have the pi phase shift. So we move on to the next value of m. For m equals 2, we get 1.5 divided 1.5 times 650 nanometers divided by 2 times 270 nanometers, which is equal to 1.8, which is above that, so that's a valid answer. We have now found the 2 lowest possible values of N2 for this situation, and we are done with both parts of the problem. Thank you for watching.